Okay. So in this lecture, we will try to define what is exact differential equation and how do we, if it is not an exact form, how do we make it. But before that, we need to go through the concept that some of you have already studied, and then let us just recall that in the previous lecture we have seen the equation solvable by separation of variables. So the idea is to make x m the function of fx, and then we make it in y. It is a function of y and dy, and the right hand side was okay. Then if we do this integration, then we will get the solution for the differential equation. But if we have a homogeneous case, then we have seen that y equals to vx we have substituted, and then there will be linear equation of first order. Let us discuss some more cases of this homogeneous equation just to recall. If we have a case of this form, then our target is to find out these variables a by capital A, b by capital B. So let us write as a partial fractions. With this help, we will try to solve this equation. And for case B, we will follow this form. So this is nothing new. Just apply the formula and solve the problem. Nothing much to explain. Like here, this ratio, when the ratio is equal, then we have found out the solution. So just to, I would say, verify this. Similarly, you also verify this one. These are repeated from here. And for practice problem, try to verify these results. Now, what happens if to solve this is a not separable case. If you try to separate the variables, you won't be able to do that because you will have one y dx, and there is some x plus 1 into dy would be there, and some other things will be there. So the target is to make it integrable. To simplify, our aim is to simplify form, get the simplified form, and so that integration becomes easier. Now, if you try to multiply with 1 upon x plus 1, then what you will get? Okay. Then this equation becomes dy dx minus y upon x plus 1 e to the power x times x plus 1. Okay. Now, if we can make the form in this way, actually, this remains that d dx of y upon x plus 1. If we can make this is equals to, or let us write d equals to. Sometimes we'll use the derivative form. D of this equals to integration if this is this will become e to the power x plus 1 into dx. Okay, so in that case, and also if we can multiply x plus 1 into dx, then directly if we apply this will get cancelled and then our integration will become easier. Okay, the purpose why how to get this multiplier, actually this multiplier is this factor, in fact we call it a factor. So this is known as an integrating factor, which helps us to integrate possible integration make possible. In fact, how to get this integrating factor, there is a strong procedure. There is a systematic procedure. So the integrating factor is actually denoted by, actually is calculated by of this form, e to the power p. So this is integrating factor. We'll try to calculate this function. First thing is we have to make it, if the given function, the differential equation, first order linear ODE, first we have to put it in this form, okay, where p and q are functions of x but not of y. Okay, they can be function or they can be constant also. There is no formula, but they cannot be function of y. Now, if you multiply both sides of this equation, then we can write in this form d dx of y times e to the power p, e to the power integration p dx equals to, this is nothing but e to the power. Okay. Now the equation will become of this form. So if you just integrate here, you take this dx here. Okay. So d of this quantity, if you take integration, then it will become, so dx plus c, some integrating constant. And this particular is called as e to the power p dx. Integration p dx is called integrating factor. So what the solution is now? We have to multiply with y times integrating factor equals to the q times integrating factor times the dx. So this is c, integrating constant. Now if you just try to apply this formula, this integrating factor, so first task is to put it in the standard form, dy dx minus 1 upon x plus 1 y, this is e to the power x into x plus 1. Okay, our standard form is dy dx plus py equals to q. So this is our standard form. Now here we have p equals to 1 upon x plus 1 minus negative sign is there. So the integrating factor, the factor that we need to multiply with the whole equation, it is e to the power minus p dx. So for that we need to calculate e to the power minus 1 upon x plus 1 dx. So this is nothing but e to the power minus logarithm of x plus 1, which is again nothing but 1 upon x plus 1. Okay. Now if you the solution is given by y times the integrating factor equals to q times the integrating factor into dx plus c integrating constant. So in our case we have y times x plus 1 times q is our right hand side. So this is our q function. So e to the power x to x plus 1 times we have now 1 upon integrating factor is this one x plus 1 into dx plus c. So this one and this one gets cancelled. So we have e to the integration e power x dx. So this is nothing but y times y by x plus 1 equals to e to the power x plus c. So that's our answer for this differential equation. Okay, now if we have the working rule for this method is this way. So step 1, convert it into of this form. Then find the integrating factor. And then step 3 is, so then the solution is given by this function. So this is only for first order. Remember, first order linear ordinary differential equation. So similarly, you can verify this one. Example 2. So you need to put it into the standard form. So here is our p. This is our p. And then you calculate the integrating factor and you multiply it. And then try to find out the integrating factor. Similarly, you can verify this one also. So the standard form is this one. And here you can find p equals to this one and q equals to this one. So integrating factor you get this way, and then you can try to find the solution of this form. The working rule is step 3. Here you can see that we need to make some substitution so that the integration becomes easier. So yeah, that's how we will get the final solution. Similarly, for your practice problem, try to verify them. There is nothing difficult actually. So just put the formula, apply it properly, and do the calculation carefully. Then you will get the answer. So nothing much to explain here. Now, when it is we have y to the power n, remember it is not linear, because for linear case we have seen that y, y dash, y double dash, and all these things are degree will be 1, or it is not a degree should be 1. But in this case we have degree is more than 1. So this is not a linear. And this particular equation is known as Bernoulli's equation, which can be reduced to linear form by suitable substitution. The substitution is given by this form. Okay. So for this substitution, if you make it, then the problem becomes of this form. Now it is in the z variable. So z is our dependent, x is our independent variable. So this becomes linear equation, and it can be easily solved by previous method, by integrating factor method. So in order to get some example, so some practical example, if you can check it, verify it. So verify the result. Just put it into the formula, apply the formula, okay, put it in the standard form, apply the formula, calculate this uh, integrating factor, and just do it properly, step by step. So nothing much to explain here also. These are just application of formula. But this substitution is very important. What would be the substitution actually? What we need to substitute? Similarly, as a exercise, you should verify this also. If you go through it, you will understand. Nothing much to explain here. Then again, this is another example. Try to verify. So it is in the polar form. Try to verify this also. Yeah. So this for practice problem, you again verify these results. Now there is another concept called exact differential equation. So whenever we have m dx plus n dy, and these are functions of x and y. So it is not kind of mx plus dx plus ny into dy. It is not like that. Here the functions are already in terms of x and y. Plus n equals to some, for example, I mean, right hand side, oh, it is 0. If the right hand side, the equation of this form, then you cannot apply integration directly because these variables are there, no? And here also you cannot take that as a constant. When they are actually exact equation, then the working formula of this form. Now, when they will be called exact, if they satisfy this relation. So take the partial derivative with respect to y for m, and the partial derivative of n with respect to x. If both of them are equal, then we call it a exact differential equation. Okay. Now for this exact differential equation, our solution method is to find out in this way. So step 1, integrate m with respect to x, keeping y as a constant. Remember, it is not a generalized method. It is only applicable for exact method, exact differential equation. And then integrate with respect to y only the terms of n which do not contain x. And then step 1 and step 2 results are added. We make it a constant, so integrating constant. So this is our working rule. For example, let us try to solve this problem. Here we have m dx, here we have n dy. equals to 0. So m of x comma y equals to 5x to the power 4 plus 3x square y square minus 2x y cube, and n of x comma y is 2x cube y plus, not plus, this is minus. So here it is 3x square y square minus 5 y to the power 4. See, the task is to verify whether this is exact or not. So let us calculate del m del y. So from here, del m del y is, this is 0 plus, here from here you get 6x square y minus 6x y square. And for this one we get del m del x. Here you get 6x square y minus, here is a x square is there, so 6x y square plus 0. So we can see that del m del y equals to del m del x. This is satisfied, hence the given equation OD is exact. For the exact equation we need, so step 1, recall step 1 is integrate m with respect to x keeping y as a constant. So here it is, integrate m xy into dx with respect to x. So in this case we have integration 5x to the power 4 minus, not plus, this is 3 x square y square minus 2x y cube into dx. So if you integrate it, remember y is a constant here. Now assume y is a constant. So in this case we will have the integration is, so 5 x to the power 5 by 5 plus 3x square y square, sorry, this would be cube by 3 minus, there will be 2x square by 2, again y cube. So we'll have x to the power 5 plus x cube y square minus x square y cube. So this is for step 1. Now for step 2, what we need to do is we calculate step 2. So for step 2 it is given integrate with respect to y only those terms of yn which do not contain x. So in this example, in our case, we have n of xy equals to 2x cube y minus 3x square minus 2x cube y minus 3x square y square, and we have 5 y to the power 4. So we need to calculate, remember, calculate the portions which are not containing x. So this quantity has a this component has x. This component also has x, but this one do not have x. So for that we need to integrate minus 5 y to the power 4 with respect to dy. Okay, we will not consider this case. So here we have minus 5 y to the power 5 by 5. So this is going to be minus y to the power 5. Step 3 is result of 1 plus result of 2 equals to constant. So from the result 1 we have this one, and here we have result 2. So x to the power 5 plus x cube into y square, x cube into y square minus x square y cube, okay, and then plus y to the power 5 minus y to the power 5 equals to c. Or in the next line you can write minus y to the power 5. So this would be our given exact solution. No, sorry, exact solution. No. This is our required solution for the given exact ODI differential equation. Similarly, you can verify this one. So you need to find out m. What is n? Try to find out these two values. Then make them verify. This is exact. So if you can verify, once it is verified, you apply this one, the formula. So in this case, there is no term which do not have x. So that is why in this case we have to take 0. Because both the terms m and n have x in the both components of the n are having x variables. So that is why. Yeah, step 2 is the terms of n not containing x. Here both the term, here we have only two terms. Okay. Both the term are having x variable. But in the previous example, see, here we have first, there are three components. But in this component, we do not have x. Okay. So that is why we have taken this one. The terms of n not containing x. Okay. Okay, so if you apply this formula, there is nothing. You just need to find out carefully m and n, and after that you just put it into the formula. Then you are done. Yeah, tell me. I did not get your question. Okay, tell me. Yeah, yeah, homogeneous. Yeah, that is true. Homogeneous is okay, but homogeneous approach is in that is for plus two level actually. There are equations for which you may not be able to verify whether it is homogeneous or not. If you can guess, or if you can find the multiplier properly, okay, then you can do the integration. In fact, these equations just for our discussion. The simple examples may not be there in the actual problem. We may have some difficult problems where it is difficult to verify whether it is homogeneous or not. What you have observed is correct, but the idea is here different. The concept is to verify that whether it is exact or not. You can always solve it as a homogeneous equation. Okay. The idea is to study the exact differential equation. So similarly, if you can, yeah, for this type of example, if you multiply, if you try to apply a homogeneous concept, that may not be easy to apply. So in that case, this approach for exact after checking the exactness, you will be able to find it the solution easily. So for practice problems, try to verify these examples. Yeah, Sachit Anand. So far, I do not have any idea about it because I have not seen anything, any textbook like following that one. You may find some other textbook, but which I am following, they are actually giving this approach. So yeah, better not to go any other approach. So this is a standard approach actually. Okay. Most of the textbook follow this approach, so that is why I am discussing in this approach. So for exactness verification, there can be some that may not be exact, and by suitable integrating factor after application, that can be made into exact equation. For example, if if the fraction is a function of x alone, then fx, and say fx, then the integrating factor will be this one. Again, this actually kind of apply the formula and then solve the problem. Nothing much to explain. The only thing you just have to remember that under which condition we will apply rule 1. There are several rules that I will discuss one by one, and that some particular examples are also given. Okay. Example and practice problem. So for this problem, you need to calculate. Okay. The thing is, the question that many students ask me about this, sir, how do we know that this is going to be a function of x? So that whether we'll apply rule 1, 2, or 3. In that case, it is actually, it will, the practice will make you to feel that which rule is going to be applicable. The more you practice, the more you get the idea. There is no specific, this is unfortunately, there is no specific rule, there is no specific way to determine that rule 1 is applicable for this type of problems. Okay, so then if you have this problem, then you can. The thing is, given the problem, you need to understand that whether it is applicable, the rule 1 is applicable for that or not. So for that, you just need to verify this quantity. If this quantity is a totally function of fx, then you can apply this one. So all this idea you will get through exercise and practice. So here the function is actually completely function of x. For example, then the integrating factor. Remember, the integrating factor helps us to simplify the ordinary differential equation so that our integration becomes easier. Ultimately, our target is to integrate and find the solution. So if our steps are simplified, if our equation is simplified, then we can just directly take integration and then solve. But identifying this multiplier is very crucial step. So that is why we need to follow some well defined structures or well defined rules and regulations for the given differential equations. So that is the main motive of today's lecture, that we need to find out the well defined structures. Similarly, you try to verify these problems related to rule 1. In fact, you try to verify this may not be, after starting all the rules and approaches, you may find some, for this problem you can apply rule 2 also. That can be happen, but try to apply as the sequence is given. Okay, so if this quantity is a function of y alone, then the integrating factor will be this form. So when we have found the integrating factor, we will multiply it to find the solution. Okay. So once we get it, this is a function of y, and then we try to find out the integrating factor. We will multiply the exact equation. This is m dx plus n dy. But in this case, see that second term, this is n. Okay, in this n, we have here x. We have x here also. So this will be deleted in the finding the solution. So that is why only 2y is given. Now once you find it, exact equation, when the function is not, when the given equation is not exact, okay, it's not exact, then you need to make it exact by suitable multiplier, and this multiplier is the integrating factor. So whenever you have this exact differential equation, the next step is very simple. Just assume them as a constant and just apply. See, this whole term is a constant, and we have only one x outside. And from here we have y square dy, because we have deleted this step 2. In the step 2, we'll eliminate x and x terms in the n function. So these are nothing much difficult. So try to verify the other results also. There is another form. If we have m is of this form, y times f1 into xy, and n has a x times into f2 of xy, then the integrating factor will be this form. Why integrating factor needed? Because we want to make it exact form. Once we have exact form, then by step 1, 2 and 3 rule, we can find the solution. So remember, this is very important, the given condition. If m has the form and n has this form, so if we have this xy form, then we can directly apply the integrating factor. So this would be the integrating factor. And in this case, again we apply the exact differential equation. From there you apply step 1, 2 and 3, then you get this solution. So try to verify. And these are your practice problems. Okay, so rule 4, it says if the variables, the functions are of this form, and of this form, the differential equation has of this form, where the integrating factor is actually x to the power h and y to the power k, where you have this relation satisfied. M plus h plus 1 equals to n plus k plus 1 divided a by b. So this is our a, this is our b, yeah, and h will be the particular. M is given, n is also given. So this will be clear if we have one problem satisfied. So here in this case, M, H, A and B is given. M dash, N dash, A dash and B dash are given. So in this case we have this relation satisfied. Here H and K are unknowns. Okay. We have to find out from here and here. H and K are unknowns. We need to find them. From these two equations, so two equation and two variable, we can easily find out. So this is one equation, this is another equation. So we can, after solving, we get this one. So the integrating factor will be this one. Okay. So this is our integrating factor. Now we have integrating factor. So this integrating factor will be multiplied throughout the equation. Once you do that, it becomes exact equation. So now after finding the exact equation, you will have this one as m and this one as a n. So m dx plus n dy you have, and then you apply the formula. There are step 1, 2 and 3. So for step 1 you assume y as a constant, and for step 2 if there are no x, there are no term which contains actually x, then it will come. So in this case both the terms of n are having x variable. So if x are there, then 0 dy. So in order to make that this will contribute 0, so that is why we have taken only the first one, and it is has given the solution. Okay. So in this way you get another example. For example, to try to verify this equation also. So here also you get, so this is our n, this is our m. So m dx plus n dy, and here this becomes a exact equation, and then you step apply step 1 to 3, then you will get this solution. And these are your practice problems for this rule 4. Okay. Okay. Now there is another rule which is called rule 5. If the equation is homogeneous form and m dx plus n mx plus ny is non-zero, then this is going to be one integrating factor. Okay. Like Sajid has asked that we can, whether we can make it in exact form or not by homogeneous equation. So if this is a homogeneous case, then we can apply this formula, and here integrating factor will be this one. Once you apply this, once you multiply this exact equation, so integrating factor, then equation becomes exact differential equation. In case of exact differential equation, you apply step 1 to 3, and you will get the solution. So there are some practice problems. try to verify them. In fact, there is nothing much to explain. Is that just apply the formula, whether they are actually satisfying or not. If they satisfy, apply this formula. If they are not satisfied, then try other formula. That's how it is. It will work. Nothing much to explain here. The only thing you need to practice. Then only you will get the idea. So that's all for today. I'll stop here.